So in lecture 1, we are going to look at some of the basic definitions which we will use in optimization. So essentially in the first 4 lectures, which includes the current lecture, I'm going to basically introduce the optimization problem, look at a statement of the optimization problem in the mathematical form. Then we are going to discuss Taylor series expansion, which will play a very big role in gradient-based optimization methods. We'll introduce the concept of the quadratic forms. Then we are going to look at optimality criteria for unconstrained optimization and for constrained optimization. And finally, we are going to summarize these 4 lectures. Now, essentially, optimization is a branch of applied mathematics. And here we want to find the best or optimal value of a quantity. Now, this particular desire to find the best value or the best solution is prevalent in all branches of knowledge. Therefore, you will find that the application of optimization methods is widespread. And this use of optimization method permeates engineering and science, as well as fields such as business and management, where it takes the specialized form of the subject known as OR. Now, one of the main problems in using optimization is to pose a practical design problem as an optimization problem. And this task requires considerable expertise and domain knowledge. So essentially here, domain knowledge means the knowledge of the subject you are working with. For example, if you are working with a problem on structural design, you need to know all the details about structural design. Similarly, if you are using optimization in supply chain management, then you need to know all the aspects of supply chains and so on. Now, once the design problem has been expressed as an optimization problem, you can use a bunch of tools to solve this optimization problem. And in this particular course, I'm going to discuss some of these tools. So optimization can be thought of as a collection of tools which essentially solve the optimization problem once you have expressed it in a standard form. So the first 4 lectures are going to discuss this particular set of tools. And beyond that also, we are going to continue on the tools, but using more numerical methods. Now let's state the optimization problem so that we do not have any doubt about it. So essentially, so that all the people are on the same page, we have defined a standard form of the optimization problem. So here essentially what you do is you minimize the objective function f of x. So which you can see here, f of x. And this function is in general a multivariate function of n design variables. So you see x1, x2, x3 to xn. Now, if you are only minimizing this function, then you have what is known as an unconstrained optimization problem. But typically most practical problems will have constraints. And therefore you have what are known as the inequality constraints, which we are referring to here by g subscript ix less than equal to 0. And we see that there are m of these constraints, 1, 2, 3, all the way up to m. And similarly, we have p equality constraints, which we denote by h subscript jx is 0. And then here there are p of these. So j is 1, 2, 3, all the way to p. Now, you may ask, what about the case where some of the constraints are given in greater than equal to form? So if that happens, if you have a constraint in this form, capital G jx is greater than 0, then you can actually write it in this form here by multiplying both sides by a -1. So that is going to simply result in a constraint in the less than form. Now, like I mentioned before, if you do not have constraints, you have a problem which is known as an unconstrained optimization problem. but most practical design problems are constraint optimization problems. But one of the reasons to study unconstrained optimization is that many constrained optimization methods are based on extensions of unconstrained optimization methods. Now, in many situations, we can convert constrained optimization problems into unconstrained optimization problems using what are known as penalty methods. So in these penalty methods, you typically add a term to the objective function, and this term tends to become larger and larger depending on the violation of the constraint. So essentially, the objective function is penalized for constraint violations. Now let us look at some of the aspects about the constraint space. So one of the things you can immediately see is that the number of equality constraints must be less than the number of design variables. And here I am talking of constraints which are independent. So essentially, if two constraints are dependent, that is, in some sense they are parallel lines or parallel planes, then of course they are going to be redundant to some degree or to all degrees. But in case that is not so, then this particular situation holds, because if you have such a system, then the equality constraints can be solved for a solution. And this is often used as a trick question in homeworks and assignments, that you can get an optimization problem where actually the equality constraints can be solved for a solution, in which case the objective function plays no real role. Now, the second possible situation could be that there are more equations than unknowns. And here the system is an overdetermined system of equations. And this means that there are actually redundant equality constraints, or the problem is inconsistent. So probably you need to go and check the formulation of the problem. Now, as far as the inequality constraints are concerned, there is no restriction on their number. Now, one more name for optimization which is often used in the mathematical branches is linear and nonlinear programming. And essentially, optimization came out of mathematics to a large extent, and therefore you will see in mathematics as well as computer science these terminologies also being used. And here essentially linear programming is defined as a problem where the functions f, h, and g are all linear in terms of x. So again, recall that here f was a objective function and h and g represented constraints. So if the objective and the constraints are all linear, we essentially have a linear programming problem. Now, if a single of these functions are nonlinear in terms of x, then you have a nonlinear programming problem. So again, the methods which we use for solving linear programming and nonlinear programming are quite different, because linear programming is better to solve by various methods which use the fact that these problems are in a different type of situation and essentially are much easier to solve in many cases because of the benefits provided by the concept of linearity. So essentially in these linear programming problems, you are dealing with straight lines and planes, and therefore the mathematics for these is quite different from what you have for nonlinear programming problems. Now there is an important concept known as feasible design and the constraint set. So basically we can say that a collection of all feasible designs is called a constraint set. And the constraint set is essentially a set of all the points x which satisfy the constraints. So here you can see that x is such that h are all satisfied and g are all satisfied. Now, a point x which is in the constraint set is known as a feasible design. So feasible designs are all the possible designs which a designer can choose and which are actually legitimate for the problem. Now, one of these designs is going to be an optimal design, or in some case there may be more than one such design. But finding the feasible design itself can often be very important, because if you have found a feasible design, then you can use one of the points from this set as your design solution. So the constraint set defines this feasible region. So this entire collection of points X which satisfies the different constraints is known as a feasible region. And many times you will see in papers or design studies in optimization that people will try to figure out this particular feasible region and to plot it in simple two-dimensional or one-dimensional cases. Now, one of the important facts, of course, is the optimal point must lie inside the feasible region. Now, constraints can be sometime active at a design point, and essentially this happens if the constraint is satisfied as an equality constraint. So essentially here we are talking of a constraint such as G, and here instead of being less than 0, it is becoming equal to 0. In that case, the constraint has become active constraint. Now, for a feasible solution, such a constraint may or may not be active, which essentially means that G may be less than 0 or G may be 0. But as far as if you look at the H constraint, these constraints must all be satisfied for a feasible design, because by definition H must be 0. Now we look at some of the possibilities of the design variables. Now the way we have defined the optimization problem, we can see that the design variables are typically continuous values, and therefore we are looking at the space of real numbers. Now this may not be the case at all times. So you may have a situation where a design variable is discrete, and this happens if its value can be selected from a finite set of values. For example, we may have piezoceramic patches of thicknesses such as given here 0.25, 0.5, 0.75, 1, and so on. Now, essentially this may be because of commercially the thicknesses which you can get from some supplier belong to this particular set, and therefore it is useless if you give a design such as 0.37 millimeter thick patch and so on. So your design algorithm should essentially search for solutions within this discrete set. Similarly, if you are designing composite structures, you have certain design variables called ply layups. And again, for ease of manufacturing, it may be prescribed that these can be plus minus 45 degrees, plus minus 90 degrees, and 0. So this again is a very restrictive set, and you do not want the optimization method to give you various numbers in terms of continuous design variables here, because if you take those values to a manufacturing person, that person may say that I cannot really manufacture those kind of laminates. Now, one more situation happens if the design variable is an integer. For example, if we are talking of number of bolts used in a mechanical system, materials being present for design. So maybe we have a set of materials which we can select for a particular design. And again, you can select one material or the second material. So we can classify all these by some numbers. Similarly, we may have a number of airfoil sections which we are using for wing design. So we may classify different sections here as 1, 2, 3, and so on. So again, the optimizer would have to search this particular design space, which is not expressed in terms of continuous design variables. Now, whenever you use these kind of integer or discrete design variables, you will get additional complications for the optimization problem, because typically we are assuming that functions are continuous, and therefore f of x is a continuous function and x is a real variable. And if that does not take place, then you need certain different type of methods to solve your problem. And some of the problems which lead to these kind of situations, they can be solved using subject known as integer programming. Now, if you have many simple problems, they can be solved graphically, and in many optimization situations, you will find that people plot simple functions of f of x versus x, and then they can find out what is the feasible region and how to get the minimum or maximum point. So essentially, they plot the contours of the functions, the objective function as well as the constraints, and they find the point in the feasible region where the objective reaches a minimum value. But the problem with graphical optimization is it's typically limited to 1D and 2D problems. Now, as far as optimization methods are concerned, we can broadly classify them into two types. The first type of methods is the optimality criteria method. And this is sometimes known as the indirect method. Second type of method is essentially based on a search of the design space, and this is known as the direct method. Now, these criteria which are there are actually conditions a function must satisfy at its minimum point. So we will see some of these necessary and sufficient conditions which a function must satisfy for the minimum point to be classified as an optimal point. Now we look at the concept of global minimum and local minimum. See, a function of n variables has a global minimum at x star if f of x star is less than the f of x for all x in the feasible region. Now, if this value is pure less than and no equal to sign is there, then it is a strong global minimum. Now, if you have a function of n variables fx where this particular situation holds only in a small neighborhood of x star, then this is known as a local minimum. So that's the big difference between the local minimum and the global minimum, that this holds in the feasible region and this holds within a small neighborhood of x star. And x star is the symbol we are going to use in general for the candidate local minimum point or the global minimum point. Now here you can graphically see the concept. So for example, I have plotted this general function f of x with respect to x, and you clearly see that there are two possible minimum points here, A and C, and here C would be a local minimum because if your optimization procedure is somewhere here in the vicinity of this point, it's probably going to think of C as the local minimum point. But if you have a situation where you can search the entire design space here, then A would come out as the global minimum point. Now in this problem we have two constraints here, x is A and x is B, very simple constraints, and so all this set of values within this region A and B is essentially known as the feasible region. So all these points are in the constraint set. Now you may also get sometime a maximum point, so here you can see this is clearly a global maximum point here. And you can also see that these particular points are also stationary points of the function, and essentially the slope of the function is 0 at these points. Now there are some mathematical theorems which can help you. The Weierstrass theorem is there, which gives a test which can be used to determine if a function has a global minimum point. And this test states that if the function f of x is continuous on a feasible set S which is closed and bounded, then fx has a global minimum in S. And a set is closed if it includes all its boundary points, and each sequence of points has a subsequence that converges to a point on the set. So again, the definition here includes the fact that the set S is closed and bounded, so you can see the definition closed here. And then the next fact is the boundedness, and the boundedness means that if you have any point x which is in set S, then xt x, which is x transpose into x, the dot product, is less than C, where C is a finite number. So essentially this particular distance measure is bounded. Now, whenever Weierstrass theorem is satisfied, the existence of global minimum is guaranteed. But if it is not satisfied, there may still be a global minimum. So this theorem essentially predicts the fact that there may be a global minimum, but it doesn't let you know how to find it. Now, one of the very important concepts in optimization is the gradient vector. And essentially the gradient vector, which we will use as C, sometime it's also referred to by this reverse delta symbol here. And this is essentially a collection of the partial derivatives of the function with respect to the different design variables. So we essentially take the objective function f, which we want to minimize, and we take the partial derivatives with respect to the design variables x1, x2 all the way to xn, and then we formulate the gradient vector. So essentially this gradient vector is actually a column vector, but we sometimes write it as a row vector and put a transpose here because in books you want to save space and so on. Now, essentially the way I have written this gradient vector here, this is the gradient vector of the function f of x at x star. So x star is probably a candidate minimum point. Now, there are some interesting facts about the gradient vector. The first is the gradient vector is normal to the tangent plane at point x star. Secondly, the gradient vector points in the direction where the function is increasing the most. Therefore, negative of the gradient points in the direction of maximum decrease of the function. So that's something very important to remember. And this particular fact is used in the steepest descent method, where essentially you simply go down the path of the negative of the gradient to decrease the function. Now, corresponding to the gradient, there is one more fact which we use here, which is essentially the second derivative in multi-dimensional form. So we will assume that the function f of x can be differentiated twice, then you can form this particular matrix. And this particular matrix H here, you see that essentially you take the partial derivative with respect to x1 and you take one more partial derivative with respect to x1. Here you take it with respect to x1 and then with respect to x2 and so on all the way to x1 to xn. And again, by nature of the theory of partial derivative, this matrix comes out to be symmetric. So the H matrix is a symmetric matrix, which you can see here, H is equal to H transpose. So these two matrices will become, this matrix and the vector will become very important when we look at multidimensional Taylor series, which is something which we will use in optimization very frequently. Because for many nonlinear problems, we do not want to retain all the possible terms of the Taylor series. We can generally approximate a nonlinear problem by the first couple of terms, which is essentially the linear approximation and the quadratic approximation, and that is where the C vector and the H matrix will come in. So this essentially ends our lecture 1, and I will see you in my next lecture. Thank you very much.